This video will certainly not be boring. The model of the Bohr atom is the simplest way of understanding electron behavior and the energy within an atom. It's actually the most common isotope or version of the hydrogen element with merely one proton and one electron. It's composed of an infinite number of circular rings called energy shells, which are non-continuous or discrete in their spacing about the nucleus. They are also called electron energy shells because they constitute all the possible places an electron can be within an atom. With merely one proton as the nucleus and one electron, the only charge-related force in play for a Bohr atom is the attraction between the positively charged proton and the negatively charged electron. It's because of this attractive force that the electron doesn't doze off from the atom because the nucleus has a grip on it. According to the law of electrostatic attraction, oppositely charged particles will form an attractive bond with each other, and the strength of that attraction, the tightness of that bond, is related to their distance of separation, and this distance is called radius because our Bohr atom is a circular model. So using this law, these two terms are inversely proportional. So the smaller our radius, the stronger the force of attraction between our electron and proton together. So based on this principle, how can we describe an electron occupying the shell closest to the nucleus? Well, by definition, it's got to have the smallest possible radius. So that would mean that our nucleus has the strongest possible grip on the electron, so that electron is as stable as can be. Broadly speaking, energy is defined as lack of stability. So higher stability means lower energy. So with the most stable bond holding the electron to the nucleus, our electron will consequently have the least possible energy within the atom. This is what's called a ground state electron, meaning the electron is as close as possible to the nucleus with the minimum energy possible. We'll expand upon this with our Bohr atom's single electron and the energy levels it occupies. We denote our shells with the letter N and assign it a whole counting number, 1, 2, 3, 4, etc., where the numbers increase as we get further and further away from the nucleus. As we can see, N equals 1 corresponds to the ground state. Let's take a cross-section of our atom to really see how this works. We have our single proton nucleus and the energy levels which ascend as we move further and further away from the nucleus. The use of whole numbers for N serves to organize the electron shells, providing a clear indication of their sequential arrangement relative to the nucleus. For example, when comparing the N is equal to 4 shell to the ground state, it's evident that the former is positioned farther away from the nucleus. It's like saying Mars is the 4th planet from the sun and Mercury is the 1st. There's no such thing as the 2.37th planet from our sun. For the Bohr atom, our one electron can potentially occupy any one of these shells. So because electrons occupy these shells, they take on however much energy is associated with that shell. So if the electron is in the 3rd shell, it's going to have as much energy as what's associated with the N is equal to 3 shell. Furthermore, the further away the electron shell or level is from our nucleus, meaning higher N values, the larger the energy associated with that particular shell. This means that an electron occupying a higher shell will have more energy than an electron occupying the ground state. Beyond this, while energy increases as N gets higher, it does so at a slower and slower rate. That's what's called logistical growth. That's why we see each successive shell-to-shell jump associated with a smaller increase in energy than the one before. And consequently, we flatten out as we get N approaching infinity. So there's actually an equation that allows us to model the nature of this increase, but also calculate exactly how much energy each electron shell has. It's equal to a negative constant divided by the square of N. Which graph best depicts energy as a function of the energy level N? This might seem very daunting at first, but process of elimination makes this beyond doable. Firstly, we know for a fact that A and C are wrong answers because energy of these shells is discrete, it's non-continuous. Also, D can't be right because we know that energy must increase as N increases. So, B is the correct answer. By zooming in, we can see how this fits all of the features we've mentioned for electron shells. Energy is discrete, 1 dot per shell. Energy increases as N increases, and that increase gets slimmer and slimmer each ascending shell-to-shell jump. What's new is the realization that these shell energies are all negative energies, which means that the energy of our ground state, which is the smallest energy, is actually the largest negative possible. So our x-axis functions as a horizontal asymptote because as n gets infinitely large, E gets infinitely close to zero. This is what it means to be a free electron, completely unbound by the atom. The energy is zero because there is no force between our electron and our proton. So did you learn the following? 1. A Bohr atom is a type of hydrogen atom with only one proton and one electron, and that makes the purposes of studying electron behavior super simple. 2. There is an attractive electrostatic force between the proton and electron, the strength and length of which has consequences on the energy of that electron within the atom. Lastly, electrons occupy discrete energy shells modeled by this graph and this equation, and it tells us a variety of things, mainly that the ground state electron shell has the lowest energy possible, the largest negative energy value.